for here. For Liz, it's already being made. Next time. And everybody wants to take it. Oh, did you? Okay. Okay. Well, hello, everybody. A gift to you. Okay, I'll take it. How's everyone doing? Definitely take it. Good? Good. Hi, Casey. No Rich tonight?
No, he's in Oklahoma City, either running from the law or.
Oh, yeah, that sounds very suspicious.
What did you do to deserve to be there? You just doing like weekends?
See what happens when you miss a meeting? You get trashed. It's just about 6:30, so we'll get started here. So welcome everybody to the April meeting of the Stockton Astronomical Society. I look around the room and on the screen, and other than our guest presenter, I see everybody's a familiar face, and we don't have any guests tonight. A couple of announcements before we get started. Our new policy is to keep the back door locked all the time. If you need to come in, if you're going to come in the back door, expect that you have to knock and wait a moment for somebody to open the door for you. Pat Lehman is our door monitor. Let's give Pat a hand tonight. Yeah.
About to get back.
Okay. So I think you have to pay Pat a fee if you want to get back in. Other announcements. We have a whole group of announcements after the presentation and the Q&A. So at this point, I think we're all set. Everybody online ready to go? Okay. Welcome, everyone. Hello, Michael. I know you've got to jump off at 7:30, so I hope you enjoy the presentation up till then.
Thank you. Thank you. Yeah, I wish I could stay longer, but I got that class at 7:30, so unfortunately I have to leave early, but thank you.
Thanks. Okay, well, with that, I'm going to turn it over to Eric to introduce our speaker for this evening.
Thank you, Tim. Hello, everybody. Our speaker today is Dr. Juliette Becker. Her talk is going to be on exoplanetary architectures and ultra-short period planets, classifications and dynamics at the inner edge. Quick bio. As of fall 2023, Dr. Becker moved to Wisconsin to join the University of Wisconsin-Madison. There, her group will focus on solving questions related to planet formation, like how do planetary systems attain the architectures that we observe, and how does the protoplanetary disk influence the geometry of maturing planetary systems. As part of the Wisconsin Center for Origins Research, their group will also attack questions relating to the origin and persistence of life on exoplanets. For the past 4 years, Dr. Becker has been a 51 Pegasi B Fellow at Caltech. There she worked with Professor Konstantin Matigian. I forget if that's how you pronounce his last name, but he had spoke to us back in 2022 on Kuiper Belt objects. They worked on an assortment of dynamical problems in the solar system and beyond, including how disk properties and stellar variability affect planet evolution. She was a National Science Foundation Graduate Fellow at the Langweber Center for Theoretical Physics, Graduate Fellow at the University of Michigan, where she obtained her PhD in astronomy and astrophysics. Her advisor there was Professor Fred Adams, and during her PhD research, she studied the dynamics of both exoplanetary systems and of our own solar system, and led the discovery of 2 new planets in the WASP-47 system and a trans-Neptunian object in our own solar system called 2015 BP519. Dr. Becker is passionate about unraveling the mysteries of exoplanetary systems. Her research focuses on the life cycles of planets around both our own sun and other stars, exploring how planets form, migrate, and interact with each other. She investigates the dynamics of multi-planet systems with a focus on understanding the outlier systems that appear to subvert existing theories of planet formation. She's also interested in how habitability is affected by dynamical evolution. And if you want to see more of her publications, you can go to the Harvard Astrophysical Data System and take a look at her other publications. So please welcome Dr. Juliette Becker, everybody.
All right, great. Thank you so much for that very robust intro. So can you see my slides okay?
Yes, we can hear you fine.
Okay, great. Slides, you can see those as well.
Yes.
Okay, great. So today I'm going to talk about mainly one topic, which is exoplanet architectures and how you sort planets into architectures, how it's been done historically and how we're trying to do it now. And then at the end, I'm also going to delve into one specific system geometry. So ultra short period planets, which is kind of the shortest, as the name implies, it's the shortest period planets that have been discovered in the exoplanet population. And a little bit about how we can try to understand this one population of planets. So what I'm hoping that you guys will take away from this talk today is that there are a broad number of exoplanet populations that are not present in the solar system, and there's a lot we don't understand about them. So what I'm going to start with is the solar system. And I have here an animation. So we're going to, right now there's the 6 planets that have been known since antiquity on this. The x-axis is the orbital period, so how long is the year on this planet? The y-axis is the planet mass. As the years ticks by, you're about to see the discovery of Uranus, which happened in the late 1700s. And after another 100 years, we'll see Neptune pop up on this plot. So this is basically the historical pre-1990 or so story of planet discovery. So 6 of the solar system planets, the terrestrial planets, and then Jupiter and Saturn are, as you guys I'm sure know, visible with the naked eye. Uranus and Neptune were both discovered only once technological advancements and mathematical advancements got to the point where they could be discovered. So Uranus was discovered with telescope-assisted observations. And Neptune is a pretty special case where its existence was predicted by mathematics by a guy named Urbain Le Verrier. And then he predicted where in the solar system it should be. He sent a letter to Berlin Observatory, who then looked in the place he said it was and found Neptune and formally discovered it. But each of these 2 discoveries, which were in 2 different centuries, in the 1700s and the 1800s, were the results of decades up to a century of work since telescopes were first invented and then subsequently improved in the early 1600s. So this is kind of the state of planet science and our understanding of planet formation up until fairly recently in the 1900s. And one thing that people immediately tried to do with this set of planets that were known, and you'll notice that I'm leaving Pluto off here because it's no longer a planet, even though we thought it was a planet for a little bit over 70 years. But one thing that people tried to do with the set of planets, as small as it was classify it and try to understand which of the planets were similar to each other. So I'm going to show you a example of one of the major classification schemes that's been used for these planets since we've known about them. And what I'm going to use to show that is actually an animation from a kids show on PBS. So usually when you try to sort the solar system planets into categories, people sort them into the inner planets and the outer planets. And these categories actually seem pretty robust because the inner planets and outer planets have differences both in size. The inner planets, Mercury through Mars, are significantly smaller than the outer planets, both in radius and mass. In composition, the inner planets tend to be made of rock and other objects that have high sublimation temperatures, while in the outer solar system, you have things that are made bulk of ices and hydrogen and helium. And now, as we've started to advance our understanding of planet formation theories, we also think that there's similarity in how the planets form. The inner planets, which are mostly rocky, probably formed in a similar way at similar timescales. And the outer planets in the outer solar system, Jupiter probably formed in about 1 million years, and all of the outer planets experienced some migration post-formation. So this is a pretty simple classification scheme, but it's actually pretty helpful because it helps us understand what are the similar histories that different groupings of planets, the inner versus outer planets in our own solar system have. But this is a talk that's not a 2-minute talk, it's an hour talk. So I'm not going to stop here at the solar system planets. I'm going to move on next and talk about exoplanets. So you guys probably have heard many talks on exoplanets before, but just to define what an exoplanet is, an exoplanet is just a planet orbiting outside of the solar system around any star that is not the sun. So our population of planets in the solar system only numbers 8, but outside of the solar system, there are many thousands, millions, even billions of planets waiting to be discovered. And so if we want to construct a similar classification system for the rest of the planets in the universe, not just our own solar system planets, the first thing we have to do is discover those planets. So I'm going to really briefly introduce kind of the two main discovery methods that have been used so far to discover planets. So first, there is something called the transit method. And the transit method functions by monitoring the starlight that you receive from a distant star and looking for dips in light as a planet crosses in front of the star. So in this animation, you'll see this top panel here is an image of what the star would look like on the plane of the sky if you were a telescope looking at it. Now, caveat, we generally cannot actually resolve stars and see them in the way that you see this in the animation. So when a telescope observes a distant star, it looks like just a single pinprick of light in the sky. And then in the lower panel, you see if you were monitoring the amount of light that you got from the star over time, what would that look like when a planet passed in front of the star? And there's this kind of characteristic dip shape that has a flat bottom and then this kind of gradual ingress and egress where the planet passes in front of and then leaves the plane of the star. And this shape encodes information about not only the planet's orbit, but also its physical properties like its radius. So the transit method has been used very successfully in the past about, I guess now 20 years or so. There was really an explosion of transit discoveries in 2009 with the launch of the Kepler Space Telescope. And the Kepler Space Telescope's entire survey strategy was to scare at 100 square degrees of sky and just monitor as many stars in that 100 square degree patch as possible, looking at their light, just monitoring it over time, and looking for dips like the one in this animation. Following Kepler's retirement and eventual running out of fuel, which it finally closed the doors on its extended mission in 2018, there's currently another transit hunting spacecraft called TESS, the Transiting Exoplanet Survey Satellite, which is using the exact same strategy, but surveying stars across the entire sky instead of just in that 100 square degree patch that Kepler was looking at. So, takeaway from this is just that transits is a method that has been used very successfully to find planets. It can only find planets that happen to pass very serendipitously in between the distant star and us, the observer. So there's a limitation to the types of planets that can be found. And if you're trying to find not just single exoplanets, but you're trying to find planetary systems like the solar system, then you need to see not just one planet passing in front of this line of sight, but you need to see multiple planets, which requires a geometry kind of similar to the solar system, with planets being all in roughly the same orbital plane. Now, this is not the only method we've used to discover planets. So far, this is the method that's found the highest number of planets. But number two, the second most prolific method so far, has been the radial velocity method. So the radial velocity method is the method that actually discovered the first known exoplanet around a main sequence star, which you guys have probably heard of, 51 Pegasi b. Myself, my postdoc fellowship that I did at Caltech was named after this discovery because it was really the beginning of modern exoplanet science. And in 2019, that discovery earned the two discoverers, Michel Mayor and Didier Queslov, the Nobel Prize in physics, which was pretty exciting. The radial velocity method functions by, instead of looking for a planet to cross in front of a star, like kind of in the lower left panel here, instead what you're looking at is you're looking at the star spectroscopically. So instead of looking at the total amount of light, you're taking spectra repeatedly over time. And by doing that, you can measure the star's motion along your line of sight. So is the star moving towards you? Is it moving away from you? If a star has a planet bound around it, then just as a star exerts a gravitational influence on its planets, so too do those planets exert a gravitational influence on their star. So this animation here is showing how a star and a planet orbit around their center of mass, rather than kind of the conventional picture is, well, planets orbit around a star and the star is stationary. That is actually technically never true. So the star is also orbiting around the center of mass of the system, where that center of mass is computed with everything that's in the system, stars, planets, everything. Generally, so this animation here is kind of a vast over-exaggeration of how much a star would move. But stars do move up to something of like an amplitude of maybe 10 meters per second for a slightly further away Jupiter, up to about 100 meters per second for a hot Jupiter. So a hot Jupiter being a Jupiter mass planet orbiting with an orbital period of only a couple days. So lower right panel here is showing how the dotted lines here are the true locations of spectral absorption lines that you might see in the star's atmosphere. And then the moving black lines show as the planet orbits around the star and tugs that star back and forth along our line of sight, then what is the spectrum going to look like? And what you'll see here is that there's kind of a periodic motion in these spectral lines where you see them first blue shifted to bluer wavelengths and then red shifted to redder wavelengths. And if you observe a system for long enough, then you can actually, just like with the transit method, back out orbital properties of the planet as well as physical properties, because it is the mass of the planet that determines how much the star is going to move. So I've only introduced 2 methods of exoplanet discovery. There's a few more methods that I don't have as much time to talk about today. So one of those is direct imaging, where you basically block out the starlight coming from a star and try to take an image directly of a planet around the star. And you can either take that image in reflected starlight, or if the planet's young enough and hot enough, you can take a spectrum of its own, or take an image of its own emission. And then there's also microlensing, which I don't even have time to go into a short description of. But in addition to these kind of big 4 methods, there's a whole bunch of smaller methods that have been used to discover just a few planets. So next, I'm going to show you kind of another historical timeline of these exoplanet discoveries over time. So same style as before, x-axis is orbital period, y-axis is planet mass. These new discoveries are going to be color-coded by how they were discovered. So I just talked over the discovery of 51 Pegasi b in 1995, but you can see that a lot of the early exoplanet discoveries from 1995 until the early 2000s were all radial velocity discoveries. And that's because this is a really successful method to be done from the ground. Starting in after 2009 with the launch of the Kepler Space Telescope, you start to see these big explosions of orange points. Each of those is another release from the Kepler Space Telescope. And then after 2018, the new transit discoveries are now coming from TESS, which is the new transiting exoplanet discovery telescope. So the animation now stops in 2024. And this, we have now over 5,700, we're kind of approaching 6,000 exoplanets that have been discovered now. What you'll notice from looking at this plot is, because I've also overplotted here the solar system planets, including Jupiter, as well as Uranus, Neptune, and then the terrestrial planets down here. What you'll notice is that the exoplanets that have been discovered are kind of not the same as the solar system planets. So in the solar system, we had this picture of the inner system that had these small rocky planets, and then a gap, and then the outer system that had these large gas giants made of hydrogen and helium in bulk. But you'll notice that for all the terrestrial planets, as well as for Uranus and Neptune, most of the exoplanets that have been discovered don't actually look like those planets. They tend to have larger masses, so they're higher up on the y-axis, as well as having shorter orbital periods. Now, before I jump to how we can classify these thousands of data points, these thousands of exoplanetary systems, I want to point out that part of the reason for this is observational bias. We don't actually think that there are not planets like Earth and Venus and Mars out there in other planetary systems. We think that the reason that we haven't found them is just that our technologies are not yet good enough. So the signals that you find using both the transit method and the radial velocity method are going to be a lot larger for larger radius and larger mass planets. So that means that if you're higher up on this chart, it's going to be proportionately easier to detect the planet. Similarly, if you want to get a signal over a long time baseline, the orbital period tells you how long it takes for one orbit of the planet to be completed, which means that if you're trying to study things that have orbital periods of like a year or more as we get further out in this plot, you're going to need a lot longer baseline of data to actually recover that orbit. So what this means is it means that we are actually pretty early on in exoplanetary science. We are now just barely entering the beginning of having 30 years has passed since that first discovery of 51 Pegasi b. As time goes on in the future, hopefully we'll fill out this chart more. Now, the next thing that I'm going to move to is our actual classification scheme. So just like in the solar system, where it kind of is helpful to know about inner planets versus outer planets and the differences in properties that those have, we also think that having a classification scheme for this huge number of planets will help us understand the similarities as well as the differences and help us identify when something in the sample is weird. So I'm going to, on the next slide, produce the classification scheme that a collaborator of mine, Alex Howe, who's a scientist at NASA Goddard, and me and a couple other collaborators, Chris Stark and Fred Adams, put together to try to make order of this mess of points that you see on this plot. So here is the big plot of this classification scheme that summarizes the entire scheme. So this classifies almost all, and I'll get to that if we have time at the end. I have one slide of that little asterisk of almost, but almost all of the exoplanet systems that you saw on the previous slide. So to start with kind of the boring ones, for one planet systems, we classify those essentially by planet type. So you can have a single Jupiter, which just means when we say Jupiter, we mean it's a planet with a mass and radius similar to that of Jupiter. You can have a single Neptune, analogously, a planet with mass and radius like Neptune. You can have a single sub-Neptune, which is just a planet slightly smaller than Neptune's radius, larger than Earth's, or you can have a single Earth. And we aren't classifying anything smaller than Earth because we just don't have discoveries in that regime. So kind of Earth or slightly smaller than Earth-sized planets are really the smallest that have been discovered in the exoplanet population. Slightly less boring is two-planet systems. So in two-planet systems, we essentially break these, and no longer are we considering every possible permutation of planet radius. Basically, the dominant difference in two-planet systems is a planet a Jupiter or is it not a Jupiter? And the reason for this is that Jupiters have a very different formation pathways than all of the smaller planets. So Neptune's through Earth's, Neptune being like 16 times Earth's mass, probably form mostly similarly in a way where if you're an Earth, you form via accretion of rocky planetary embryos. If you're a Neptune, you do that to make a core, but then you also accrete some gas, some hydrogen and helium from your disk. Jupiters go through a process called runaway accretion, which is a very different process and grows them up to be about 300 times larger than Earth. And this is kind of a very different pathway for a Jupiter mass planet than for the rest of the planets. So these are kind of, we consider them different and special. Moving on, there are a couple different types of now architectures for multi-planet systems. If you only have one or two planets in the system, you can't really classify the architecture of the entire system as a whole because you're only seeing one planet. But once you start to have three or more planets, then you can start to classify not just the planet properties by the mass and radius of the planet, but you can actually characterize what the architecture looks like as a whole. So for example, in our own solar system, we have 4 inner planets that are small, and then we have 4 outer planets that are large. And that's not actually something that we see in the exoplanet population, mainly due to probably observational bias. So a couple kind of special architectures that we have here are inverted mass ratio systems. So this is something where you might have a small planet like Earth, a large planet like Jupiter, a small planet like Earth, and then a large planet like a Jupiter. And then there's also this category that I'm going to get back to at the end of ultra short period planets. So this is planets where you have a system that has, some planets, but there's one planet that's extremely close to the star, and it's the year on this planet is a day or less. So we think that this is a particularly special type of exoplanet system. It appears that these systems have had a very different evolutionary pathway than the rest of the population. But I'm going to put a pin in that and get back to ultra short period planets later on in the talk. Now, the right panel of this plot is really where things get interesting and kind of where our classification scheme starts to show the differences that you see in the exoplanet population compared to the solar system. So you'll see here that we have these two groupings of inner planets and outer planets. And this is kind of the same base definition that the solar system taught us was important. It does appear that in the exoplanet population, there is a difference and a dichotomy between inner planets and outer planets, although the boundary between those two categories is not necessarily exactly the same as in the solar system. So the types of exoplanet architectures that we see here are first, something called peas in a pod system. So peas in a pod system have multiple planets of very similar masses. So you'll see this, these animation here includes Earths and sub-Neptunes and Neptune-sized planets that are kind of similar in mass. None of them are those large Jupiters that form in a different way. And inner planets can either be closely spaced, where you kind of have even spacing between the planets, or you can have a gap. And if you have a gap in the system, there's three different places the gap can be. It can be in the outer part of the system, the middle part, or it can be in the inner part of the system. And then finally, so these are four different gap styles you can have for peas in a pod system. Each of these different system combinations can also have an outer planet, a Jupiter in the outer part of the system. Next up, the other big category besides peas in a pod systems is warm Jupiter systems. And warm Jupiter systems are just defined by they have a Jupiter mass planet that's in a warm orbit. So something that is not within 10 days of the star, but maybe within 10 to 100 day orbital period. And we think that this is a distinct category from the peas in the pod systems, because unlike the peas in the pod systems where planets are kind of similar and probably formed similarly in the same part of the system, which is what we see in the solar system, in these warm Jupiter systems, the Jupiter formed very differently and probably had strong downstream effects on the properties of the other nearby planets. And then finally, any of these planet types can have, so the closely spaced, gapped, or isolated Jupiter hosting systems could potentially also have a Jupiter in the outer system. Finally, last category is a cold Jupiter system, where you have some number of cold Jupiters in the outer system and you don't see anything in the inner system. And this particular category is probably very underpopulated right now because it's not our transit and radial velocity discovery methods, which have been so prolific and good at discovering these planets, are not great at finding these cold Jupiter systems. So it's really direct imaging, which is a method that's kind of picking up steam, and future missions will focus more on direct imaging discoveries, but we really haven't filled in that part of the diagram yet with discoveries. So this is the ultimate classification scheme that we came to looking at the sample. To get to this classification scheme, we had about 5,700 planets available as of September of last year. Not all of these planets were suitable for including in the classification scheme. So we took out about 73 of them for various reasons, including they had incomplete data, they were planets around white dwarfs and neutron stars, or they were around a brown dwarf, not a real star. Brown dwarfs are small enough that they're not fusing hydrogen in their centers. So these planets were just tossed out of the sample because they didn't fit our criterion of understanding the architectures of exoplanets around main sequence stars like the sun. Next, there were a good quantity of systems that did not have sufficiently good quality data to be categorized. So for example, if we didn't have a good radius or a good period measurement of the system that was reliable, then we couldn't classify it. That left us with about 4,200 systems that were good to categorize. And these planetary systems, so this is around 4,200 host stars. And these could have either a single planet, or about 900 of them had a multi-planet system. So you had more than one planet orbiting the same star. And then of this subset, about 300 of those had 3 or more planets. And characterizing exoplanet architectures, again, it's helpful if you have a larger number of planets in a system so that you can actually tease out the differences between system architecture types. So now I'm going to walk through a couple of the things that we thought through when trying to create that classification scheme that I showed you. So the first is this idea of the inner-outer divide, which is kind of the same thing that people identified very early on about our own solar system. This idea that there's an inner solar system with coherent properties, there's an outer solar system with coherent properties, and then a gap between them. So a question that we had is that something you see in the exoplanet sample? So this plot here is, again, on the x-axis, we have the orbital period in days of each planet. Now, the y-axis is labeled by name, and each of these names here is a different host star in the exoplanet catalog. So, for example, in this top row here, the HR 8799 system, if you follow along the line here, then you'll see dots corresponding to each of the known planets in the system. So this particular one was actually discovered via direct imaging, and this is our only example of 4 cold Jupiter mass planets. But each of these other systems, you can see the discovery method color-coded. So you can see the vast majority of planets in these multi-planet systems that we're using to do these classifications are coming from those 2 methods we talked about, the transit method and the radial velocity method. So these are ordered, these systems all, I should say, importantly have detected Jupiters, and they're ordered kind of approximately by geometry. So up here, you can see there's kind of this line of Jupiters where these systems have Jupiters at shorter orbital periods. These ones have Jupiters at longer orbital periods. So they're sorted by where the most interior Jupiter, so the one in the shortest period orbit, is located. These systems up here that have Jupiters at longer orbital periods, so a year is something around here. So a lot of these have orbital periods of around a year or more than that. One thing that you'll notice looking at this population is that there appear to be these gaps in these systems where you have a Jupiter that's far out in the system. And these blank spaces mean that no planets were discovered in that regime, but then you have planets in these systems that are closer to the host stars. So these are not really solar system analogs, but they're kind of suggestive of the geometry we have in our own solar system of an outer Jupiter and then a gap between that and the inner system. Similarly, if you look down at the systems that have the Jupiters with the shortest orbital period, you don't really see the same gap. So there's something different between these 2 sets of populations with inner Jupiters and outer Jupiters. So the real question in a classification scheme, because you can see from this plot that this is a continuous distribution, right? There's not like a clear population of systems that have outer Jupiters that are far away and systems that have inner Jupiters that are close in. There's like kind of a continuous distribution. So with so many systems, this means that if we're interested in understanding what separates these systems from these systems, it means we have to figure out where in this intermediate range you should put a boundary to separate out the 2 classifications, the 2 categories. So how do we do this? Again, this is something where we have a limited amount of data right now. So we're kind of doing the best we can with the planets we've discovered. You can tell that there is a really noticeable split of these outer systems that have gaps and these inner systems that do not have gaps. So if you do have up here like a Jupiter at greater than 100 days, then it looks kind of like the solar system. You have a gap, kind of like the Mars-Jupiter gap. If you have a Jupiter at less than 100 days, these planets down here, then there's no inner gap, and instead there's a good number of planets on either side of the Jupiter. So what we kind of took away from this population of planets is that there's about a boundary of 130 days that kind of separates these 2 populations, where you have the gaps up here and you don't have the gaps down here. But I will point out this is arbitrary, right? This is just what we see from the data that we have right now. It's very likely that if we return to this classification scheme in 10 years, where hopefully we have many thousands of more planets, we're going to get a different answer for exactly where the boundary is. So as always, astronomers love to say we just need more data. We need more planets. Next up, you might be curious of exactly, in our own solar system, what does that inner-outer divide look like? And if you do the math of what the solar system period ratios are, then between Jupiter and Mars, you get this large 6.3 period ratio, which is much larger than the period ratios between each other adjacent pair of planets. So we kind of were inspired by this, and we constructed a classification scheme. So here is the table that gives you we've talked about this visually, but here's the actual numbers. That defines systems as being gapped if they have separations of roughly more than that Jupiter-Mars gap in our own solar system. So the two different categories here are closely spaced systems, where you have planets that kind of occur evenly in a line, and gapped systems, where you have some gap somewhere in the system that's analogous to the Jupiter-Mars gap and separates one grouping of planets from another grouping of planets. Now, you might also be curious about, okay, well, where is the gap? Is it kind of a middle gap, like in the solar system, or is it an inner and outer gap? And at least with the data we have now, it actually appears that it's more usual to have a gap in the inner or the outer part of a system, where you have one planet separated from the rest of the planets in the system, than to see something exactly like the solar system. Now, I will point out again that there is a observational bias effect here as well, because if the solar system were an exoplanet system, we would not actually currently be able to discover all the planets. So the systems where we are actually discovering these gaps are not necessarily solar system analogs, since we couldn't have discovered those. Now, one other interesting thing that came out of the characterization scheme that we developed was kind of other features that appear commonly, but do not actually set the entire geometry of an architecture. So now we have a few more categories of systems where we see a decent number of systems to share a similar property. So one of these categories is a hot Jupiter. So hot Jupiters are just Jupiters that are orbiting within 10 days of their host stars. I'm going to skip ultra short period planets because I'm going to get back to that in a second. So super puffs are planets that have anomalously low densities. So densities lower than 0.3 grams per cubic centimeters. Some of these planets will actually have densities of less than that of styrofoam. So these are hard to explain, but there's actually a decent number of systems. And then finally, strongly inverted mass ratio, that's the alternating between like an Earth-sized planet and a Jupiter-sized planet, and so forth, that I mentioned before. Then you can characterize these into either evenly spaced systems, so peas in a pod system, because there's a bunch of planets that have similar properties, similar masses and similar radii to each other. Or you can group these into warm Jupiter systems, where you have at least one planet that's the mass of Jupiter. So basically the left column here is systems that don't have a Jupiter in it, and the right column is systems that do have a Jupiter mass planet in it. Now we'll return to one particularly interesting subset of this classification scheme, which is ultra short period planets. So ultra short period planets are particularly interesting because they sit at the boundary of the parameter space. So ultra short period planets are defined as those with orbital periods of less than a day. So on this plot of all of the planet discoveries that have been made up till now, they are essentially everything to the left of this axis point right here of 1 day. And there's actually a decent number of ultra short period planets. They are actually surprisingly easy to find with the transit method. So you'll notice that most, but not all, of these planets were discovered with the transit method because they have orange points on this plot. They are surprisingly easy to discover because they orbit their star in such a short amount of time that if you observe them continuously with a telescope, you will have very frequent events. So if you were observing this, you would see the planet transit faster than once a day. So you can build up a whole lot of signal very quickly compared to like the lifetime of the Kepler mission or even the TESS mission. Now, we can plot the geometries of systems that contain these ultra-short period planets. And now this is the similar plot to before. The x-axis here is the orbital period of each planet in the system. And then the y-axis is the name of each exoplanet system that we have discovered to host an ultra-short period planet. So this line right here on the inside is the actual ultra-short period planets themselves. And then all of these other points in the system are extra planets that occur in the same system as each of these ultra-short period planets. Now, ultra-short period planets, they kind of took up a lot of space on that plot of exoplanet discoveries. And they are very close to their star and easy to detect in transit, as I just told you. However, if you do correct for the fact that they're so easy to discover, they actually appear to be pretty rare overall in the galaxy. We think only about 1 in 200 stars hosts an ultra short period planet, as compared to maybe like 1 in 3 that hosts a multi-planet system. So these are actually pretty rare. The other thing that makes them a very interesting subset of the exoplanet sample is where they actually orbit. So because they are so close to their host star, so they orbit in less than a day, which usually means that they are only a few stellar radii away from the star itself. So actually, I have an animation for this. So an ultra short period planet, again, is about 1 to 4 times the stellar radius of the star away from the star's radius. So this is actually like somewhat to scale with the size that I've made the star on this slide of how close the planet size is not to scale, but the separation is to scale. Like this is roughly how far away proportionately an ultra short period planet would be to its host star. And this means they're very highly irradiated. And there's a few like really unique geometries that we found because of how close their stars are and how highly irradiated they are. So a few cool examples of this are, so these are just examples of ultra short period planets that have been found that were on those previous spots that we looked at. So TOI 2109b has, we think, a surface temperature of about 3,600 Kelvin. So this is very hot. There are actually some stars that have effective temperatures pretty close to this. And it's just basically getting baked by its host star. Kepler 78b is another example that's about 3,500 degrees. And then there's one of my favorites, which is KOI 1843b. So this one we think is above 3,000 degrees Fahrenheit, but we can actually see that based on its measured parameters, it's probably made just strictly of iron. And we think that it actually might be like a deformed football shaped planet, deformed by tidal forces from the star and made basically only of iron. So these are some pretty extreme geometries. And this is actually not the only way that these particular planets are extreme. So they actually exist in a place where we don't think planets should exist. So one huge challenge in understanding how ultra short period planets form is that they actually reside interior to where we think the disk could have formed planets. So in this diagram here, we have here in the central of the image is a host star. These green lines coming off of the host star are the magnetic field of the star. So stars have approximately dipole magnetic fields. So it's kind of like these look similar to what you've probably seen for magnetic fields of a north-south magnet. That's basically what the stellar field looks like at the disk edge. Around the star, first you have a gas disk. So this is a really hot region where this part of the disk is being very highly irradiated. So material here is going to be basically all gas. Exterior to that, you have a secondary disk of dust. So while this part is hot enough that this is all gas, further out you could also have some dust as well as gas. And what sets the scale here is the magnetic fields of the host star will set a radius where no gas will move interior to that radius. We call this the magnetic truncation radius. So basically at this point, the magnetic fields are strong enough that disk material will not move in. Instead, what disk material will do is it will travel up along the magnetic field lines and it will accrete onto the star. So basically, the magnetic fields are a conveyor belt taking material from the disk edge and then dumping it onto the star. And then that is ever so slightly increasing the mass of the star. The problem here is that, what do planets form from? Planets form from disk material. So if you're going to form a planet, you probably need to form it in the dusty disk where there is a solid silicate and iron material available to form planets. At the very least, you would at least need to form it in the gas disk where there's like physically material available to form the planet. However, the scales for each of these regions, the truncation radius is about 3.5 stellar radii. So 3.5 times the actual radius of the star. And then the disk edge is maybe something like 7 to 8 stellar radii of the dusty disk edge. Now, if you'll remember what I said about where ultra-short period planets are, their orbital periods are about a day, and they're about 1 to 4 stellar radii away from their host star, which means that they reside right here in this truncation zone where there should not be any disk material. Now, this has been a huge problem for understanding how ultra-short period planets could form, because basically what this is telling us is it's telling us that they should not form where we see them to be, because there would not have been any disk material present for them to form from in their locations where we see them. So what I'm going to end with today is 4 different hypotheses for how you could actually form these ultra-short period planets. And I'm presenting 4 hypotheses. One of them is one that I developed with Constantine, but I'm going to try and present them as evenly and fairly as I can, because we do not yet know which of these operate or how often they operate. So we don't know which of these are correct. Probably some of them are correct or all of them are correct in some cases, but we don't know which ones are correct and we don't know how often they actually occur to create ultra-short period planets. So here are the mechanisms, and then I'll talk through each of them in detail. So the first potential mechanism to form ultra-short period planets is called tidal inspiral. So the idea here is if you have a planet that's orbiting around a star, and it has some eccentricity, so this means sometimes it passes closer to its star than other times, then this planet can actually raise tides on its host star. And this is kind of similar to the way that the moon raises tides on the Earth, or in Jupiter and the Galilean satellites, tides are raised on the moons and also on Jupiter. So if the planet does raise tides on the star, then that tidal bulge gets carried around by the central object's rotation. This then spins down the central object and can make the planet move inwards in its orbit. If you have a sufficiently eccentric orbit, so like the closest approach and most distant approach of the planet are different enough, then the magnitude of the tides can be very strong, and this can dissipate energy in the planet's orbit. And then over time, the planet's orbit will slowly shrink. So the idea of this tidal inspiral hypothesis is that if you have a planet with a sufficiently high eccentricity, then this tidal circularization will cause the orbit to shrink over time, and potentially it could shrink enough to become an ultra-short period planet orbit. The next hypothesis is called secular chaos. So this plot here is a computer simulation showing how this method would work. So on the x-axis, you have the time of the simulation in millions of years. And then up here in the top panels, you have the basically how close is the closest approach of the planet to the star. And on the bottom here, you have the tilt of the angle. But the important thing to notice here is that you simulate, this is for the Kepler-10 system, which is a multi-planet system that has an ultra-short period planet in the system. And if you simulate the system forward, then you can basically have chaotic processes that will not always operate. So if you evaluate the same system, you integrate it forward 10 times, you won't always see this happen. It won't happen 10 times. It will only happen sometimes. But every so now and then, you will have a process that causes the planets to be scattered into new orbits. So this is chaotic. and it's caused by secular, so long period interactions between planets. So in this particular case, this computer simulation showed that these outer planets, their orbits didn't change very much. But this inner planet here that started at about 10 to 20 solar radii, through these interactions with other planets, it moved into about 2 stellar radii at the end and became an ultra short period planet. So this method requires having multiple planets that can interact with each other for this to happen. The third method is called obliquity damping. And the idea in obliquity damping is that something we haven't talked about yet is the fact that planets can have tilts relative to their orbits. So this is, again, something that we have a good example of on the Earth, right? The Earth has about a 23.5-degree tilt relative to its orbit direction. And we call this obliquity. So it's basically a misalignment between the spin axis of a body and the orbit normal of the body. And so in 2020, Sarah Mulholland ran some simulations that showed that if you had multiple planets in a system and each of them had some starting value of very carefully chosen values of obliquity, then you could basically get the planets coupling together. So Earth is pretty far away from its neighbors. So we don't have any coupling we don't have any significant coupling between our spin axis and the spin axis of nearby planets. But if you put the planets close together, so here in the initial part of the simulation, the planets had periods of 2, 2.4, 2.6 something days to start with. So it's a very tightly packed system to start with. Then the interactions between the planet's spin vectors can result in them having orbits that shrink over time in response to these spin interactions and potentially becoming ultra short period orbits. The last mechanism that I want to tell you about is one that I worked on, and this is gas drag during FU ORI events. So to explain what that is, I'm going to first explain what an FU ORI event is in case you haven't seen this before. So FU ORI class objects are named after the progenitor object that showed this type of behavior, FU ORI. Basically what's happening in these events is you have a star that has a disk that's still present around it. And previously I mentioned how disks are accreting material onto their central stars. So this is happening in FU ORI type objects. The difference is that in FU ORI objects, this happens at an extremely fast rate. So 4 orders of magnitude, 10,000 times faster than it happens around typical stars that are accreting material from the disk. And this only happens for a short amount of time. So we think that these kind of accretion outbursts last something like 10 to 100 years. And here on the left panel in this image, you can see a few plots of the visual magnitude of stars in this class. So FU ORI is a good example. I think at first, this is a brightening. So it was previous to this accretion outbursting event, it was around 16th to 15th magnitude. And then suddenly something, we are not really 100% sure exactly what yet, but something caused its mass accretion rate to increase by huge amounts, 10,000 times. And the star brightened. So it brightened up to about 10th magnitude. And then actually FU ORI, so this happened in, I think it was like 1937. And FU ORI has still in this accretion outbursting event. We think it probably will last about 100 years. So, potentially sometime soon we'll actually get to see it leave this accretion outburst state. But it's an incredibly short-lived event where the star basically just eats material from the disk really quickly. Now, what this means is it means that the disk properties during these accretion outburst events are going to change very significantly. So here's a kind of animation showing if you have a disk that has some inner edge, and that's the truncation radius set by the magnetic fields of the star. If you decrease or if you increase the strength of the magnetic field or the mass accretion rate, that disk inner edge can actually move closer to the star. Now, what that means is it means that when we look at a star and we infer where we think its truncation radius was when it's formed, if we did not know the accretion rate of the star at all points in its history, then we might actually be wrong about that. So this here is an equation that relates the truncation radius of the star to, this is just a constant scaling factor. This is the dipole moment of the star's magnetic field. M star is the mass of the star, and then m dot is the mass accretion rate of the star. So on the x-axis here, we have the mass accretion rate of the star, and then on the y-axis, we have what the disk truncation radius was. And the kind of typical value that I showed you that still of before is something like 0.1 astronomical units for a star, maybe like 0.05 for a sun-like star. But during a outburst event, an FU Ori-like mass accretion event, then that truncation radius actually shrinks significantly in size. So that means that the disk is actually has an inner edge much closer to the stellar surface than what we would expect just using kind of standard models of disk physics. What this potentially means is if you simulate what happens to a planet during one of these events, if you have a planet that kind of starts at the disk edge, which is maybe the innermost location you would expect planets to be normally, and you allow it to, during one of these FU Ori events, you allow it to migrate inwards, you could actually move it into shorter period orbits. So in this particular case, we've only simulated migration during one FU Ori outburst. It doesn't quite get your planet close enough to be an ultra short period planet, but if you had a star that had a few of these, or maybe two of these outbursting events, then perhaps you could take a planet that started at the disk edge and make it a ultra short period planet. So back to these four mechanisms of forming ultra short period planets. I don't have answers for you in terms of which of these actually operate. It's also very possible that there's more mechanisms that people haven't thought of yet that could create ultra short period planets. But this is just kind of an example of how challenging each of the sub-architecture types in this giant classification scheme are to understand. So, hopefully I've convinced you that the ultra short period planets are pretty confusing, and there's a lot we still need to understand with them. But this is only one of the subpopulations that we've actually found members of in the exoplanet sample. And so there are similar analyses going on right now for each of these other subpopulations where people are trying to understand how did they form? And eventually the goal will be to kind of put the pieces together and construct that coherent picture of planet formation that explains not just these systems, but the solar system planets and additional systems that we're going to discover with future missions like Roman and Habitable Worlds Observatory. All right, we are formally at the end of my talk, but one last thing that I want to put up is 7 oddballs, as we call them in the paper, which is systems that kind of defy the classification scheme that we've created. So each of these systems have something weird about them that means they really don't fit into our classification scheme. And what does that mean? It probably means 2 different things. One is that our classification scheme is not complete because we have not found enough exoplanet system architectures. There are more types of architecture that we just don't know about yet because they haven't been discovered. So that's probably, I think, the most likely explanation. But another explanation also is that there is something special about these systems or something that we don't understand. So I will end here on this slide, and I would love to take any questions that anyone has about any of this.
Okay, there's a microphone here. Let me hand it to you, Jeff.
That was above my brain by several magnitudes. On the gaps and some of these other things, is it possible that the reasoning could be tidal forces or just how old the system is? Maybe as the system ages, their gaps and characteristics change.
Yes, yeah. So tides can definitely create inner gaps, especially. So when you have a system with an inner gap, it could have previously looked like a closely spaced system, but then the innermost planet could have, via tides, migrated inward. So that is a possible explanation for some of the systems. Your other point of can systems change over time? Yes, definitely. So one of the things that actually a student of mine has been working on is looking at how interactions between planets can cause planets to transition between these categories. by not truly having planets disappear, but having what planets we can discover with our observational techniques change. So, for example, you could have a closely spaced system, but then say that this planet here didn't transit. And so it had a higher inclination. It was not seen in the same plane. Like solar system, everything's kind of in the same plane. But imagine one of those planets was tilted by like 15 degrees. Then you wouldn't discover it while you were observing it. But then maybe millions of years later, when it cycles back down into the plane again, you could observe it again. So there's probably some factor of observational bias creating these categories. So that's something that we're very aware of. There's cases where some of these architectures may actually really just be normal architectures masquerading as gaps, but there really is a planet in there, we just can't see it.
Okay, very good. Go ahead, Doug.
So on that note where we have things moving around, or are not moving around, but above the plane, okay? So with the transit method, obviously the distance of these stars, those planets have to be within what, 1/100th of a degree, 1,000th of a degree of from seen from here?
Yeah, it's actually not quite that bad. So depending on the separation, for close in planets, it's like 3 degrees. For
Okay.
things at like Earth's radius, it's like 0.5 degrees. But
Okay.
this is, if it was like a Jupiter or a Neptune analog that far out, then yes, it would be like way less than a degree and
Right,
really hard
so we're
to see.
catching less than out of 100 stars, we'll catch one that has transiting planets.
Yep, exactly.
Okay, all right. And
Yeah, no, that's actually like a very important point because so this is something we try to correct for. We try to say based on what we found and our like observational bias constraints, we think the true underlying population is actually X. But like if you look at this plot of discovered planets, you'll kind of notice that there's the transit discoveries have kind of a cutoff where you don't usually find planets with longer orbital periods than like the cutoff looks to be at like a little more than 100 days. And the reason for that is exactly what you're saying. The transit probability is so low, we just don't find a lot of them.
and we haven't been able to watch that star for that long.
Exactly, right. So there's a lot of actually examples of single transits from both Kepler and TESS where a planet was only seen to transit one time. And actually, one of the oddball systems, if I go back to this one, so one of these HIP 41378, so you'll notice that these 3 planets are pretty long period, hundreds of days. These were actually discovered with transits, but we first found them in, I think it was 2016. And then the community spent literally 8 years trying to, because we only saw each of these 3 planets transit one time, which means we didn't know the orbital period. We didn't know the orbit. So people spent literally 8 years hunting for these using ground-based telescopes, trying to find them again, looking at every possible time that it could be transiting. Like it was extremely difficult to find these. So yeah, you're pointing at something a huge limitation of the transit
I mean, it
method.
takes Jupiter 12 years to go around ours and Saturn 30. So, I mean, we're going to need 150 years worth of data.
Yep, exactly. Right. Yeah. I mean, that's why even now we're just starting to kind of fill in the radial velocity population because the surveys have now been going on for like 25 years. And theoretically, so a lot of times we see trends in the radial velocity that we think could be due to a planet. But if you don't see the trend actually turn into an entire cycle, then you just don't know what the planet parameters are.
Right. I have one more question if I could.
Yes.
100 years ago, when I was doing Astronomy 101, they were talking about Saturn and Jupiter actually switching positions early in our system. Is that still a theory?
It is a theory. Yes. Yes. So
theory. Okay.
it is a theory. Yeah. We don't completely understand the outer giants migration. We think that Jupiter probably did switch directions as kind of the current consensus. So like migrated inwards and outwards.
All right. I just want to see if it was still a valid theory. Thank you.
Dr. Becker, you opened your talk and you mentioned that Neptune was discovered or theorized first by mathematics. Is that no longer a valid method to identify planets?
It is actually. So it has been used both in the solar system and also in the exoplanet system as well. So the best example in the exoplanet system is something called transit timing variations. So essentially the transit method functions by looking for like the dips when the planets cross in front of distant stars. Sometimes you will see dips that occur, like if it was a single planet in a system, you'd expect them to occur evenly. Like if your orbital period is 9 days, it should occur every 9 days. But sometimes we will see systems where transits occur slightly earlier or slightly later than expected. And when that happens, it's basically exactly what Urban Leverrier did, where he looked at the position of Uranus and found that it wasn't exactly where he expected it to be. So he used a mathematical model to predict what could be causing that, and the answer was Neptune. There have actually been exoplanet examples of people looking at the transits occurring early and late and realizing, okay, there's got to be another planet in the system that we can't see that's causing this. So yes, Urban Leverrier's mathematical methods are still very well alive. And there's actually, I'd say, a decent population of planets that have been discovered that way, maybe on the order of like dozens out of the nearly 6,000 that we have.
Okay, but it's usually to find an additional planet, not the original planet that you discover by transit.
Yes, that's correct. Which is mainly because if we don't know about any planets in the system, then we'd basically just have no data, nothing to start from. Because the only thing we can really see right now, we're just starting to get to the point where we can detect the planets directly with like direct imaging. But usually you're not actually detecting the planet, you're observing the star. And so if there's not some type of signal that you can see from a planet, then you just don't know anything essentially. But if you have at least one planet in the system, then you can start to use these mathematical techniques to predict the presence of additional planets.
Very good. My other question is, does your architecture model account for any variations or different types of stars, different stellar types or generation types?
That is an extremely timely question. So this method does not, but actually Alex, Chris, Fred and I are working on a second paper that kind of expands this and does account for that. So like very, very good idea. That's exactly the idea that we also were interested in and pursuing.
Great.
I'm sorry, so you mean, is there any correlation on the Hertzsprung-Russell diagram? Is that what you mean?
Right, stellar
Okay.
types.
Okay.
Yeah. Mhm.
Yep. So as a little bit of a kind of flash forward, like it does appear that larger stars host more Jupiters and smaller stars will host more multi-planet systems. So there do appear to be some correlations with the spectral type. And as for why that is, that's something we have some inklings about, but need to fully figure out.
I see. And then you mentioned that there were like approximately 4,200 accepted systems.
Yes.
Help me relate that to the total number of systems that you might have been observing so that I can understand the percentage that have planets.
Yeah, so that is really hard to do because technically hundreds of thousands of stars have been observed total, but not always in sufficient precision or for precision baseline to really rule out planets. So I would say the current like completeness corrected rates are probably something like, we think a 30% of stars have some multi-planet system. So 1 in 3 has probably more than one planets. And then for specific architecture types, like hot Jupiters probably orbit about 0.5% of stars. Ultra periods are about 0.5% of stars. But the calculation is actually pretty hard because not every star we've observed for the same amount of time. So for example, some of the stars that we observed with Kepler, we can very securely say they don't have planets above like a certain radius cutoff. But for some of the ones that we've only observed for like 27 days with tests, there could very easily be a lot of planets that we're missing.
Very good. Thank you. Go ahead, Jeff.
We had Jeff Marcy in here a number of years ago talking about Kepler. And at the time, this is years ago, he said that what they figured was if a star is a single star, it has planets. And if it's a multiple star, it probably doesn't. Is that still kind of a thing?
Yeah, so we do think that there's a suppression rate that binary stars form probably fewer planets, and that depends on how close the separation is. So, and this is actually all pretty recent work that's happened in the last probably 6 years. So we think that if a star is a close binary, so it has a binary companion within like 50 to 100 astronomical units, then it probably has a suppression rate of about a factor of 3. So it will have 3 times fewer planets than the same star if it did not have the binary companion. If the binary components are pretty far separated, so if they're like 300 astronomical units apart, then we actually don't think that there's a suppression rate anymore. The occurrence rates seem to be pretty much the same. So I would say what he said holds up for close binaries where the stars are close together. And then for far away binaries, they kind of act more like just single field stars in terms of their planet occurrence.
So with that said, on the displays that you've shown us today, are these pretty much all single star systems?
Mostly, yes. And part of the reason for that is that, especially for the close binaries, it actually can be difficult to discover planets around them. Now, that's not to say that there aren't planets around binaries, because there are a decent number of planets around binaries that have been discovered, and some of them are in these plots that I've showed you. There's also 2 different types of binary planets. So there's circumbinary planets where you have a binary star and then you have a planet that orbits the entire binary. And then there's additionally planets in binaries that orbit only one component of the binary. So the binary has a large separation and there's a planet around one component. The circumbinary planets are very weird and they appear to be different from the rest of the population. But for planets that orbit just one component of a wide binary, they seem to be pretty normal.
Excellent. Go ahead, Pat.
Doctor, the plot that you showed, sorry, get over here. The plot that you showed, they had all the stars on it, the transit, showing both the transit and the radial velocity. If you could go back to that for a second, or if you.
Yes, let's see. It was this one.
No, the one that shows the big orange blob on it.
Okay. Yes.
Yeah. Yeah. And it just, I found that fascinating because, there's something there. I understand from a transit method, you have to look for coplanarity so we can see something move in front of it versus the radial velocity. And seeing the planet mass versus the orbital period, I'm wondering if there's a third dimension to this around distance. And so I don't know if there's a distance, our ability to judge or see between the transit and the velocity method. Is one better than another, or are all these in general kind of within the same range of distance for our viewing capability?
Yeah, so that's a good question. And when you say distance, I will interpret that as brightness, because the main thing that's limiting all of our methods is our precision on the measurements. So either our photometric precision for the light curves or our RV precision for the radial velocity. And that is essentially just number of photons determines that precision. Larger stars are kind of harder to find planets around because the planets are proportionately smaller signals for both transits and radial velocities. So for that reason, even though larger stars are going to be brighter, they can be harder to find planets around. So for smaller stars, like sun-like stars and smaller, that are we think more likely to host multiple planets, and also they're kind of quieter and the signals are smaller. For those ones, we definitely have an issue of it's a lot easier to detect planets that are around stars that are closer to the Earth because of this issue of we need photons to get precision. So this was actually something that the original Kepler mission, we had a lot of problems doing follow-up to Kepler stars because the Kepler field had a lot of stars that were really far away. And because of that, they were too faint and we often couldn't do ground-based follow-up. So you had your Kepler data, but you couldn't do ground-based follow-up to try and get additional data. The TESS mission, which is the new one that was launched in 2018 and has been taking data since then, it basically learned from this and focuses on only the brightest stars in the sky. So TESS has proportionately found way more planets around closer stars as compared to the Kepler mission did. So if you had, like you suggested, a third axis on this plot of like how far away the planets were, then what you would actually see is that the transit planets that were found like a long time ago would actually be further away. And then recently we've been finding planets closer and closer to us, which is really helpful because that means they're a lot easier to follow up from the ground.
Great. Thank you very much. Fascinating talk.
Thank you.
I have one more question about the radial velocity method. It seems to me that with that method, seeing the wobble of the star, that would be the summation of like all the mass of bodies in that system. So can you ascertain the number of planets with that method, or is it just a generalization that this is the total mass?
Yeah, so that is a great question. And basically, yes, you can, because what you'll see is there's kind of two properties that each planet will contribute to the signal. This is a one planet system. So the two properties you get are a period of the motion, which is the orbital period, and then also an amplitude of the motion, which is based on the mass of the planet. If you add additional planets in, most likely they should have different orbital periods than each other. So then you would have basically your resultant RV curve would be a combination of two sine curves basically put on top of each other. And so you can actually fit those and you can recover RV solutions for multiple planets in the same system. The only thing I'll say is that can be very difficult because we don't actually know how many planets there are. And the more free parameters you put into your fit, the easier it is to get a solution. So sometimes people will think that there's a big degeneracy between, is an orbit eccentric or is there an extra planet in the system? And so that's something where if you don't have enough data, you can be tricked. But if you have a huge quantity of data, then you can actually recover the orbits of multiple planets in the same system, because you'll just basically have two curves that look like this, like stacked on top of each other. And then you just have to figure out what the two periods and what the two amplitudes are.
So going back to what you said earlier about there could be planets in gaps that we haven't been able to detect. With this method, given like the overall picture of how much mass it looks like there is, do you have a picture of like a particular system where in the gap you think that there should be something because you see the extra mass with this method?
Yes, actually, there is an example. So there's not a huge number of examples, but there's one really good one called Kepler 20. And Kepler 20 was a gapped system that had kind of a middle gap. And the HARPS team did radial velocity measurements for a pretty long time. And they found out that the gap was actually, there was a planet in the gap. It was just slightly outside of the plane that you could see with transits. So that's the best example of where that's been done successfully to like fill in the gaps. There actually are some example systems that have gaps that are very suspicious in terms of like, you look at it and you think it kind of looks like a planet would fit there really well. But a lot of times those observations are really hard and expensive to do. So I think with how many systems we have, I think a lot of times we probably just haven't put the time into actually checking to see if there are planets there. But Kepler 20 is my favorite example of where that has actually successfully, a planet has been found in a gap.
Thank you.
On moons around Jupiter and planets around our sun, we find resonant periods. Are you finding on the multiple planets in these other exoplanets, are you finding a lot of resonance?
Yes, I would say not maybe as much as you would expect. We find a lot of systems that are close to resonance, but not actually in resonance. And that's kind of a hint that there's something that's probably been knocking these systems out of resonance. And there's actually a graduate student at Caltech who was working on this, and he had a hypothesis that it was collisions between planets were knocking planets out of resonance. But you definitely do see true resonance in the exoplanet, multi-planet population. I just maybe not as much as you'd expect given how common it is in the solar system with the Galilean satellites.
Well, maybe there is resonance and we're just not seeing all of the planets that are showing it.
That's also very possible. Yes. And there have been systems. So there's another system, Kepler 80, where it was thought to be a 4-planet resonant chain. And an additional planet was discovered actually with machine learning. And that planet turns out that it probably is in the resonant chain as well. And it's actually a 5-planet resonant chain. So I think it's completely reasonable to think that that is happening other times, but we just don't know that there is a resonance at all to look for.
Oh, remarkable research, isn't it? It's intriguing.
It's a
And
very
excellent
fun,
present.
it's a fun time to be in exoplanets for sure.
Yes. And you mentioned some new telescopes coming online. Give us a little hint of what's coming in the future for your research.
Yes. Yeah. So one really exciting one that's coming up is going to be the Roman Space Telescope. And, we'll see when that one is launched. I'm not going to jinx anything, but sometime soon, hopefully it'll be launched. And Roman is going to have both a transit search, but also it's going to have a microlensing mission. And so microlensing, I didn't talk about it all today, but basically how microlensing works is you look at a bright background object like a star or a quasar or something, and then a foreground object passes in between that distant light and you, the observer. And while it does, the general relativity bends the light around this foreground object. So it basically acts as a lens, bends the light to Earth, and we get kind of a brightening of the target. If the object that's passing in front of the distant background source has a planet, then this brightening has basically a little bump corresponding to the planet. So the Roman mission is going to discover a huge number of planets in the outskirts of planetary systems, the part of the plot that was basically empty that I showed today. So that's really exciting. And then after that, kind of the next big thing that everyone's excited about that it has not started being built yet, so it's still kind of a mission concept rather than a mission, is going to be Habitable Worlds Observatory. And Habitable Worlds Observatory will be a direct imaging mission that will directly image and take spectra of the atmospheres of, hopefully, the goal is habitable planets around nearby stars. So that's probably wouldn't launch until the 2040s, but that's kind of on everyone's eye right now in terms of that's going to be really transformative if it ends up flying.
Truly is an exciting time with all those coming online, and then the research that you folks are doing. So thank you so much for an excellent presentation, Dr. Becker.
All right. Well, thank you so much for having me.
Okay, with that, then any further questions or comments about the presentation? Go ahead. No, we've got time.
Will the microlensing project also hopefully discover Kuiper belt objects?
That's a good point. So you can actually discover objects in the Kuiper belt with lensing, and it's actually been done from the ground previously. I think, will it discover some? Probably. I hope so. I'm actually not sure how many. So I guess we'll find out. The geometry is a little bit tough there because those objects are really, really small. So I actually think the ground-based surveys might do better, but hopefully we can get some with Roman.
Very good. Well, we'll be sure to keep following your research, and the best way to do that is on your website, I assume?
Yep. Yes.
Will do. Well, thank you
All right,
again
great.
so much.
Thank you so much. Take care.
Wow, that's remarkable that we're identifying those many exoplanets. And okay.
Shall we move on to the slide?
Yeah, let's look at the announcements then.
Okay. I think those on Zoom can see our slide here. Let me move to our announcements.
Yeah, Ray, let us know if you can't see the slides that we're on the announcement slide right now. Okay, so coming up in April, the rest of April, Jeff's hosting an ATM this coming weekend, right? Next weekend, the day before Easter. Same night as the Highway 4 Star Party. And then the following weekend, we're up at the high altitude site. Probably too early to get into Peddler, but most likely the heliport. And then April 27th, this is kind of a fun event. Hope everybody could come out for it, to either volunteer or just to visit Earth Day. Quite the celebration there at Victory Park. Doug, do you have any particular comments or how you shaping up for volunteers for that event?
I'll be there.
I'll be there.
Yeah, so we need to, I mean, Eric's gonna be there in the morning because he's got the solar scopes and so forth. You said you were gonna be there in the morning? Is that?
And Rich.
And Rich, okay. So we're gonna
In the afternoon.
okay, I'll come over in the afternoon also then. And then, we have a couple, I think, Omar said he would be there. And, Irvy's mom, Anita, I think she said that they would be there too, so I'll nail down morning or afternoon.
Very good. Yeah.
I'm sorry, where is Victory Park?
On Virgin, almost near my phone.
Okay,
Hagen Museum.
okay, okay,
Think you can make that Sunday?
yeah, I'll make that work.
You want morning or afternoon?
Afternoon.
Okay.
We got some fenced up construction thing going on there. Have you noticed?
I haven't been by there in a while.
It's a mess. I don't know what's going on.
I know they're reconstructing the pool, the community pool there. It's a little ways away from the area that.
Yeah, that's a long way away from here.
Good. Okay, we kick off May with our annual potluck out at Oak Grove Park. Combination SAS social time and potluck with Striking Sparks presentations.
We're gonna be giving out Sparks go? Sorry.
TBD.
I still do not have that.
Yes, he's got it.
Oh, this is.
Well, he didn't bring it with him, but he'll have it, yeah.
Okay.
Very good.
All right,
Excellent.
we're on it.
Okay. And then as the evening moves on, we move over to set up our telescopes for astronomy in the park. And we had a great time this last weekend at Astronomy in the Park. May 17th and the 24th, the star parties. And Jeff's been doing a great job about posting the upcoming conditions and who's going to those star parties. And then we're back at Oak Grove on May 31st. That is Memorial Day weekend. So we're there though.
Yeah.
We're signed up. Okay.
Excuse me. On the Striking Sparks, are we showing up at a different time or?
I have a whole slide on that day coming up, so I'll cover that in just a moment. There's 4 upcoming school star parties that I think we're still looking for volunteers for.
That whole Parks, Omar was talking about that one.
Oh,
That's tomorrow, April 11th, right?
It is.
Yeah.
you have something tomorrow?
Cause I haven't,
May 11th. Oh, April 11th.
I see a question mark floating over Doug's
yeah,
head there.
cause I haven't had anybody say we will be there, so I haven't responded to Ben Holt and say we will be there, yeah, because it was just coming up and once again, I didn't get any answers from anybody.
So
Okay.
is it just a star party or is it a STEAM event and?
Yeah, that one was just a STEAM event and it wasn't really a
Well-
start because it had to be during the day, but
Right.
the sun hasn't even set. And they're gonna leave both on that and the 24th.
Yeah.
So basically, it's just showing up there with either a solar telescope or to just hand out information.
Doug, can I suggest you shoot out an email to the volunteer group first thing in the morning? See what kind of response you get, and that way you can respond to the school. Yay or nay.
I'm sorry, I would say if it's only one day, if we haven't told them we would be there, then I think we should just respond and say we won't be there.
Yeah, that's what I was going to end up.
Yeah.
bring it nailed down tonight so that I can tell them that I have no volunteers.
And
They're having the event no matter what. They just basically invited us to it and the email I sent them was like, if I can find volunteers to be there during basically the day, I'll let you know.
Understand.
I'm sorry, not to criticize, but if
No, you're right.
we don't have volunteers
Then we have.
within 2 weeks of an event, I would think. we
You're
should
right, I
cancel.
should have done this
Yeah.
last week.
Yeah.
Don't criticize him too harshly, okay?
He can criticize me all he wants. He does more than I do.
Last thing we want to do is for him to quit.
More than that.
Well, Eric hurt my feelings.
Last thing everyone says, I have an idea.
You learned that, didn't you?
No,
Yeah, so did I.
shut your mouth.
Okay, great. So those are the announcements. Next slide is the details of the potluck on May 3rd. If you've been to any of them in the past, this is no change from previous ones. Plan to arrive sometime between 4 and 5 p.m. We're leaving it open, but we eat at 5:30. And by 5:30, we're all hungry, so we're not waiting. But please do show up. Bring guests if you like. The club will provide tablecloths, plates, cups, utensils, cold water, Kool-Aid, little punch. And if you like anything else to drink, then bring that along. I think all the details are there in the newsletter. Looking forward to a nice potluck. The weather should be great. Striking Sparks presentation. Any questions or bring whatever you want. It's total random chaos. We'll see what happens. And if we get 10 desserts, we're gonna be real happy. So, okay. Next slide, Eric.
Mine was gonna go like 11 o'clock.
Yeah.
What's that?
Well, we're gonna be showing up at 4 o'clock. Keep in mind, it's gonna go till about 11 o'clock. That's
Yeah.
pretty long.
Yeah.
After the sun
That's
sets.
why we need to eat a lot.
Keep the leftovers there so we can snack.
Just eat quick, go home and then come back.
Okay, at the last meeting, we kicked off or re-kicked off the New Moon Challenge. And the new moon was on March 29th. Did anybody take on the challenge? Did anybody find the sliver moon?
So I got an email or a text that one of our members found the moon that night, even though it was completely covered over.
How did they do that?
How did they do that? It turns out she cheated. And therefore I'm throwing the yellow flag.
Oh, no.
And I'm penalizing her for the next challenge, which she's gonna have to wait 24 hours before she can go out and look. On the 27th.
Well, since he lives like a few blocks from my house, I really knew I couldn't see anything.
That's great.
She, as I was gonna say, she sent this to the most gullible person in the room, you know, who just bid it and went with it, you know, what can I say?
It's just on my app. And it had the exact day, so of course it was a sliver, I just took a picture of
She
it.
technically did see it.
I did see it.
Who shot that picture there?
Oh, I did.
She,
You did.
You did. Cool.
that was up at Highway 4.
Right on Diablo there.
Yeah, right in the saddle of Diablo. Isn't that pretty cool? Okay, so
Shoot, that didn't strike me the other day.
this month, new moon is April 27th at 12:30 in the afternoon.
Yep.
So how difficult is it going to be to see the sliver moon that night?
So sunset is at 19:53. Okay. The moon sets at 20:19. That means you have 7 minutes and 22 seconds to see the new moon on the 27th.
Or you could do it while the sun is still up.
If you could.
You could.
It's pretty dim.
According to the heavens above, the percentage of illumination is Zero. So your penalized 24 hours.
Okay, so
Do it until the 28th.
I think he rounded down.
it'll be the next night.
There's the old night or.
That's true too. You could do that one.
But you said the new moon was at roughly noon.
Yeah.
Oh, you're screwed either way then. Because you're.
That's true.
6 hours of sunrise and 6 hours of.
You're right, you're right. So, anyway,
No. Because we're Pacific Daylight Savings Time, which means it's at 1 o'clock is high noon, so your morning can be a hair easy.
oh, you're having that
Oh,
for 30 seconds.
At 3 seconds, huh? Okay, so everybody get out there on the 28th. Okay, forget about the 27th.
That's.
Yeah. So we have no winners for the New Moon
No, we
Challenge.
do actually have a winner, because Omar took a picture the next night.
Omar did get it. Okay,
He was the only one to take a picture of the moon and send it to me. Or actually, he just showed it to me.
During the following month and trying to shoot it during sun above the horizon might be the secret to winning.
There you go.
cheating. Huh? Yeah.
Not cheating.
So
just do it at sunstone.
Just a reminder that there's a certificate for every month that you find the sliver moon. And then if you get 12 consecutive, that's the big award that will really celebrate you then. Yeah, brand new car. So,
Actually, there's something I want to add to that thing. So I did look it up because I noticed in Sky and Telescope, there were always these, every once in a while, there'd be a picture of this little sliver of a moon.
Yeah.
And it was always the same two guys in Iran. And so I knew there was something to do with, and it's because they're still on a lunar calendar. And the religious holidays and so forth start at
new moon.
that new moon day. So they have to sight the new moon, that little thin crescent, and that's the first day of the month. So if they can't see it, like the 27th will not be the first day of the month, it'll be the 28th. And so 2 days later, 3 days later, 2 weeks later, or whatever it is, will be that religious holiday. So that's why,
Or they could get a new calendar,
what's that?
or they could start doing a different calendar.
That
Wouldn't
culture,
that be a little easy?
yeah, well, that culture's that old, so, you know,
Interesting.
that culture predates the Greeks.
Interesting.
I know in Spokane back in the mid-80s, we were trying to fulfill this Islamic calendar thing by trying to see that first moon we could possibly see.
That's what we're doing now.
And it's been going on a long time.
Yeah,
Mhm.
like I said, it's been going on, well.
I got tired of it real quick.
Next slide.
Next slide.
So anybody that's come out to one of the public outreach events in the last month, March or April, will you stand up? Stand up.
We've been
March,
Yeah.
or April.
Yeah, if you've come out in March or April. Okay, let's give them a hand. Thank you.
So we're gonna name that one Astronomy in the Jungle.
Yeah.
Yeah.
Also,
Oh, the slide cut off Doug's head on top, but,
It's the sharing thing up there.
oh,
we
okay,
got Irby there.
yeah.
Yeah,
So-
she had a blast. She wanted to thank all of us for this. Her and her mom just thought that was the greatest.
They were very enthusiastic.
Yeah.
Hey, can you go back? Yeah, right there, the one before. Yeah, this girl and the two other girls, they've got an astronomical with Lincoln High School.
Okay,
Yes.
yeah,
Hina, yeah, so she came.
Oh, uh-huh.
I was hoping to be here tonight.
I was too.
We met her at the
I was wondering
event.
if you'd bring her.
I'm curious, did anyone there? There were like 5 people that I had a STEM event a couple of nights earlier.
Mhm.
There were a handful of parents who said, I want to go to Oak Grove.
They
And I
might
was
have never
curious.
say anything.
No, okay,
I would, if they said anything, I wouldn't remember.
yeah, okay.
Because that is,
One parent, the couple with the 2 young boys, they had just been to one and it didn't seem to coincide with any of the ones that we
Oh,
had done,
maybe.
so it may have been.
May have been
George's.
that one.
They were very excited, they stayed the whole night.
Yeah.
Okay, I've got a few current event updates for you. At our last meeting was the night of the lunar eclipse. And you remember we gave up as soon as we walked out the door and saw that it was completely cloudy. Well, I went home that evening and jumped on YouTube, and lo and behold, there was a group from New Hampshire, an astronomy club there, doing a live stream with beautiful views of the eclipse as it progressed. So I laid in bed for about 2 or 3 hours there and listened in on the live stream. That was pretty interesting. And
So you took this picture like Casey did.
yeah, off the internet. That's right.
It's not. That from that thing then?
He just pulled a ball and stole one off the internet.
Yeah, I just stole this one.
Actually
It
did
didn't.
see the eclipse in Washington for about 10 minutes. I got a cell phone.
Oh, okay.
But then 10 minutes later, it was gone.
Yeah.
We got about 20 minutes.
Yeah,
It's almost 8:30.
we had.
Okay, keep going here.
Okay, next slide, please.
Take time to
So that same day, there was a solar eclipse in a different location. Yeah, no, that's the same night.
No, you can't.
No,
That's
let me,
all.
look,
Oh,
tell you
wait,
what,
wait, wait,
tell you what.
wait, wait.
be quiet, please. And if you know what I mean, raise your hand. Keep your mouth zipped. Okay, you see 2 of you. As I progress on in the further announcements, I think the rest of you will understand where that solar eclipse occurred. Okay. So next slide, please. So I don't know, we've missed the updates on some of these space missions that have been launched, but the Firefly Aerospace Company, a private commercial space company, launched their Blue Ghost mission to land on the moon. They launched in on a SpaceX Falcon in January from Kennedy Space Center, and this is the lunar lander in the clean room. Michael Warzika and I were talking because he actually worked on the Apollo program back in the day at the similarity between the Apollo lander, remember the Eagle, the different lunar landers, and the design of the Firefly, the Blue Ghost vehicle. So yeah, it landed March 2nd on the moon. There was actually 2 landings. There's one in February, but if you remember, that was not a successful landing because it landed and then tipped over because it was on an incline. I forget the name of it. Eileen, the one-legged secretary, right? So this was what we should consider, will consider the first successful lunar landing since 1972, over 50 years since we've been to the moon. So if you'd go to the next slide then, Eric. This is a picture in the upper left of the lander on the moon. And the bright glare object at the top of the frame is Earth. And that's a sunset on the moon. And the star between Earth and the sun is Venus. And that's a view kind of over the camera, on the outboard camera of the Blue Ghost taking that shot. So that's during sunset. So it landed on March 2nd. On the solar eclipse was on March 13th. So if you'd go back to that solar eclipse. For us on Earth, it was a lunar eclipse. But for the lander on the moon, it was a solar eclipse. That is Earth blocking out the sun.
From the moon.
Okay, yes.
I can see.
So it looks different than a solar eclipse because if you see the ring around Earth, you're seeing our atmosphere or the reflection of light through our atmosphere.
It'd be an annular eclipse from the moon's perspective.
You look really close.
An annular
to
eclipse.
Las Vegas, right?
What I read was that from that perspective, the Earth is 4 times larger than the moon. So the Earth completely blocks out the sun. And what you're seeing is the light that's bending over through the atmosphere.
Oh, so it is. So this is all Earth atmosphere that you see, right?
It's
Okay.
not like our corona, like it would be in a solar annular eclipse.
It's all refracted, that's all refracted light.
Right, saying it should be facing the sun and then it's over that way.
Okay, so you raised your hand, you raised your hand.
And we're oblivious here, we are.
This is just the moon, not the lunar eclipse. So from the moon, it's a solar eclipse.
But what I'm confused about is that's an annular eclipse.
No,
It's not.
it's a solar.
The Earth is this big, the sun's only about that big.
Right.
It's a
But why is there a
ring
ring all the way around it?
atmosphere.
It's Earth atmosphere.
Refraction. Whole bunch of refraction.
Yeah, it's all the sunrises and sunsets around the Earth. Makes sense now? It was a lunar eclipse on Earth, but on the moon, it was a solar eclipse.
It's all just in your
The
perspective.
picture that doesn't make sense was with the earth and the sun. If they're that close together, the earth should be mostly dark from the moon. And it looked really bright,
We'll go to that next slide then.
right?
What is that?
The sun is over here, and the earth is here, and you're here. Shouldn't you be looking at mostly dark earth instead of that big bright spot up there?
Well, that's not total eclipse yet. The sun's still peeking out the side there.
I'm not talking anything about eclipses.
The sunset right here.
Are we talking about this photo or the
Earth
other?
should be black.
If the earth, look at, if the, yeah, there should be. Well, yeah, that's a big bright spot up there is the earth, which should be much darker.
But that's not the eclipse moment. That's like
No,
the day before the eclipse.
Right, but Jerry's still saying that it should be dark. But what I read was that Earth's surface brightness, what is it called? The albedo?
0.30.
What's the name of it? What's the word for it? The
Albedo.
albedo, yeah, the albedo of the Earth is so bright that it's glary like that in this exposure.
Okay.
That makes sense now? Somewhat?
I also have a problem with that photograph, but it's.
But I mean, it looks as bright as the sun.
But I'm talking about the other photograph, with the actual.
What was the sun? Which one was the sun?
It's a sunset.
Okay.
It's
this
a
one.
sunset.
So where is this light from the side casting the shadow coming from?
The cameras.
No, it's coming in. Cause there's just a little bit of the sun still peeking over and coming over.
Yeah, surface terrain.
There's no atmosphere to scatter. and things like that.
Look at the sun's behind us.
No, I have a problem with it.
Yeah,
But the other one, you're okay with that.
I haven't thought about it yet. This one got me,
Okay, right there, that black circle is the dark Earth. The
Okay,
sun is shining through the atmosphere around it.
okay.
And it's not a complete eclipse yet. Diamond ring is what it is. But the Earth is this big, the sun's only about that big. It's got a little bit sticking out there.
Right.
Okay, Eric, so the lunar landing was filmed by its onboard cameras, and I thought it was a intriguing, remarkable short video. So Eric, if you play that for us now, the Earth is the glary ball in the background. Yeah, go
Do
ahead.
you want to hear the audio?
Yes, please.
Okay, let me stop sharing. I need to reshare with the audio.
Jeff, I could explain what the problem was with the picture that you had an issue with. They spent all their money getting the moon, the camera was crappy.
Here it says, in the text that went with the article, it said that on average, the Earth is 3 or 4 times as reflective as the moon. And so it's overexposed in the images. And the lunar lander has gold foil on it. That's real gold foil because that's the most excellent reflector of the infrared light. And you'll see as it lands, it appears to flap in the wind. But as we know, there's no air on the moon, but it's due to the vibration of the vehicle. And then also look as it lands, it kicks up dust, and then after it's landed, you can see the dust settle, the 1/6 moon gravity at work there. So let's go ahead and play the video.
Blue Ghost Riders, the path to the stars is no longer limited to nations alone. Firefly is building the road to the next frontier, one mission and one dream at a time. Tonight, we didn't just reach another mission milestone. Together, we created a moment in history.
Khan, Chief Engineer on Ops. They all select the landing. We're on the moon.
So what I understand is Firefly's mission is to provide a service-based model to land instrumentation on the moon for other missions that can use that data and that instrumentation. So that was pretty cool that we're back on the moon. Yeah. And did you guys hear that Sonny and Butch are home? Yeah. Did you watch the splashdown? Yeah, that was pretty cool. I was listening to a podcast. They interviewed Butch, forget his last name, the pilot, and he said they were down to one thruster on the Starliner left, and they didn't know if they were going to, as they approached the International Space Station, they were either going to abort the mission if they put it on autopilot and let the computer, because with all the problems they were having, the computer would have shut the mission down and aborted and returned them back to Earth, which would probably have been more dangerous since they were down to just one thruster by that time. So they had more problems that came out in that interview than what we were led to believe. They really had some problems docking with the space station with the problems they had on the Starliner.
Never owned up to the truth on anything.
Yeah. And there'll be an investigation whether they get to the root cause of it or not, whether we ever see another crewed mission on Starliner is anybody's guess. Yeah, so I think that's the end of my slides, isn't it, Eric? Ah,
This one.
this is Eric's slide. Who's got it? All right. Well, leave this slide up, Eric, and I'm going to proofread mine. Casey, get a chance to proofread yours. I mean, I checked them all. I've got them all.
I just wanted to point out that you didn't specify in here that the words couldn't overlap or be within other words. So because of that, sun was in there 3 times.
There were 3 suns, huh?
One in Uranus, one in Venus, and then separately a sun.
Okay, good observation. So, thank you, Eric, for providing that word scramble in the newsletter. So, okay, we have refreshments tonight, courtesy of Dr. Mike and Susie Lavieri. Thank you very much. And anybody else have anything else to add, comment?
Yeah, we need to wrap these up sooner to give me time to pack up.
Okay. We'll help you. Okay, with that.
But later in April, there's going to be a conjunction with Venus and the Moon, and they're both going to be
Oh, in phase? In phase?
Yeah.
I'll figure it out later.
And so you could get them in, I mean, I have the date by different, if you could, I mean, why didn't Lynn couldn't actually, my camera would be able to show that, but if you took separate pictures of the.
We have a projection visible here. I'll get it next time.
Send me the dates and I'll put an email out prior to that so we can all.
Definitely.
Very good. Well, thank you all for attending. We'll look forward to seeing you at the next events. Good night.
You know, I'll enjoy it.